and then recently I joined American Medical as a clinical application specialist. So today I am here to present you on ASV. Of course I am also new to this, so it is also in terms of learning for me also it is new. So what exactly ASV is? As I already explained about ASV, and you have a little insight of it. We will just go in terms of the part of ventilators, what exactly it states. So we are going to cover the definition and exactly how it is different from other modes, other conventional modes, what we are using in the machines, in the Dragon or in GE or some other machines. And moreover, what exactly are the main parameters we set? Okay, what is the main logic behind the ASV in terms of the algorithm? Okay, how are we going to define the targets and the limits? And how are we going to use it? Ultimately, we will have also a small rough idea of the monitoring in the ASV graph, like already she explained. So we are going to cover all that part in brief. So exactly what ASV is, it is an advanced closed loop of ventilation, and it is also designed to, it's also designed to provide the user set minute ventilation with an optimal breathing pattern based on the lowest work of breathing and the minimum of the force of the breathing principle, as already explained. Now this, when we say, is it just a mode like how we have a volume control or pressure control? Okay, of course it is a mode, but it is say combination of all the modes together, which we are going to see in the slide. So in terms of the simplified ventilatory settings, so it is one mode for all the patients. Okay, so when we have volume control mode, or when we have pressure control mode, or when we put the patient on a SIMB mode, okay, it can combine for all the modes and we can use this mode. So it can be used for patients who are spontaneously breathing, and it can be used for the patients who are not spontaneously breathing, who are passive patients in short. So we can use this for both passive and for active patients. So only three parameters we usually adjust. So first is the percentage of the minute volume, PEEP, and the FiO2. So exactly the question comes when we say controls, when we talk about percentage of minute ventilation, how exactly it works. So we have set number of initial patient demographics which we set, which is the patient height, and with that it calculates the ideal body weight. Okay. Now how the ideal body weight what we set is going to help us achieve that minute ventilation. So as per the patient age, so say we have an adult patient. So we have a set coefficient for adult and pediatric patient. So for adult patient, usually the coefficient is 0.1, which is exactly 100 ml per kg of the weight. So suppose if we have an ideal body weight of say 70 kgs, okay, and if you multiply with the set coefficient of 0.1, which is usually taken for adults, so it becomes around 7 liters per minute. So when we set 100% of the minute ventilation, that means it is going to deliver for a 70 kg of ideal body weight of the patient around 7 liters per minute of the minute ventilation. So this is exactly the algorithm works behind. So as I said, when we usually talk about ASV, we say that it is for the active patient, it is a volume targeted pressure control, and for a passive patient, for a passive patient it is a volume targeted pressure control, but for an active patient it is a volume targeted pressure support. So this is how it exactly works in ASV for all the patients. So here, as said, in control or assisted or for spontaneous ventilation. So this is exactly how they have mentioned that BCV or PCV or SIMB or we have PSIMB or support. So all exactly it combines and work as a ASV. And we have an ASV pressure limit in the control settings, okay, which can be set 10 centimeters lower than the peak pressures. So whatever the peak pressures we achieve, we can set 10% lower to the ASV settings. So now when we compare it with the other modes, so we have pressure control, CMB, SIMB, and ASV. So what are the controls we used to set in this? So for pressure control, we have a inspirated pressure. Or volume control, we used to set volume. Okay, we used to set the TI-I ratio for volume control. So similarly for the support, we used to set the pressure support and the rate. So all these things we used to support, and this all used to help us for CO2 elimination. Okay, and all this were the modes. Now for all this we have one ventilator mode which is ASV, okay, and all these parameters, specifically the volume and the rate and the inspiratory time or the I ratio what we used to set, it ultimately used to help us eliminate the CO2. So all these modes, all these parameters we are just setting one parameter which is the percentage minute ventilation, and which is ultimately going to help us for the CO2 elimination. Similarly for the for the SpO2 and the oxygenation part, we have two additional parameters which is PEEP and FiO2. So exactly the same PEEP and FiO2 we have to set. So if you see in comparison with the conventional mode, for all these parameters additionally we set for volume and pressures, we have just one parameter which we have to set on the machine, which is percentage of the minute ventilation. So this is how it differs from the conventional mode to the ASV.
Moreover, when you actually do that, in the conventional mode, you need to set this maybe go back to the slide, you may need to set this 3 times in the day.
Right.
See, importantly, today if your patient calls on low compliance, high compliance and goes to low compliance, I need to set this again. I see my plateau pressures, I need to set it again. I see my peak pressures, I need to set it again. I need to do it at least 3 to 4 times in the day. Our patient does not stand straight, it actually moves. Okay, so that is why I need to set it again and again. Here, this is done on a continuous basis setting. So you don't have to keep setting it. If you are not setting your ventilator and not touching it again and again throughout your duty, you are not doing anything. It cannot be possible that your patient is a box. It's a lung. It's not going to remain the same. As you are treating, this patient is going to change. As you are changing, your settings have to change. If it remains the same, you are not touching it. You are not doing anything. You understand? Okay.
So as we said, when it comes to the control part, what we exactly said is the percentage of minute ventilation, and how do we have to start with that is before starting the machine, we will have to set the patient's height, okay, and as per that we will calculate the ideal body weight, okay, and we need to achieve, we can set 100% of the minute ventilation based on the patient ventilator requirements and the disease state moreover. So in terms of normocapnia, when the patient has a normal carbon dioxide level, and when we want to achieve when the patient is not obstructive disease, at that time we can set the 100% of the minute ventilation. But in case if you have already predefined disease condition, then accordingly we can change. Similarly, at rest we can set 100%. With the normal metabolism we can set 100%, and even with the normal lung function we can set 100%. It is said that even if the patient has fever, okay, or say small metabolic disorders in the EPG, we still have to set it around 10 to 20% higher from the 100%. So suppose if we have a patient with fever, so we can, instead of setting 100%, we can set 110%. So as said that in terms of adult, pediatric and neonatals, okay, mostly in adults we are setting it 100 ml per minute of the ideal body weight. So if the ideal body weight is more than 30 kgs, okay, then we are going to usually take 100 ml. Okay. Similarly, for the ideal body weight which is less than 30 kgs, we can take in between 100 to 200 ml per minute per kg of the ideal body weight, and for the neonates we can consider 300 ml per minute per kg of the ideal body weight. So
that is set by the ventilator.
That is set by the ventilator. So and exactly as I explained regarding coefficient. So all the coefficients are set for the adult, pediatric and the neonate in the algorithm. So 0.1 is for the adults, 0.3 is for pediatrics, and 0.5 is for the neonates. Now PEEP and FiO2 control, it is the same function setting in other ventilator mode as well, which we will have to control by us. Now it is all based on the setting of the oxygenation and the target we want to achieve. So how it is making more interesting that it is automatically selecting the breathing pattern, and it automatically and also continuously keep adapting according to that, and with that it keeps changing the as per the achieved target volume and the rate will keep changing the settings. So what is the logic behind the ASV? If you see the ASV graph, so this is already explained. Now here, since we have high respiratory rate and here we have a high volumes, So what we want to achieve here, say, is 7.5 liters of the minute ventilation, which is the target. So in that case, somewhere our safety square will be in the middle, okay, and with a rate of normal, say around 20, we'll be able to achieve around 7.5 liters. I mean, 0.7. This 0.7 liters of the volume, so which is around 700 ml of the volume which we achieve. So how exactly it works in this? So if you see this part, this is what exactly is 15 minute into the 15 rate which we want to achieve as a target. Okay, for a high rate, the volumes will be more over low, which can automatically adjusted in the respiratory lung conditions. For obstructive conditions, there will be high volume. Okay, so it will again automatically be adjusted in the machine. So we will be able to see that in the graph. So if we visualize ASV graph properly, we will be able to monitor the patient in better manner. Okay, so usually what also Ramesh Laga explained is regarding the safety square, and in the safety square lies in the middle in the square form. Okay, that means we are the safer zone. If it is a rectangular, vertical form, okay, then it will be for the obstructive. And if it is a rectangular horizontal form, then it represents the restrictive part. So automatically the volumes will be delivered less with a high respiratory rate.
So it is calculating the safety zone by actually looking at the tidal volumes and the pressure. So what it is doing is using that equation. And if it is say a restrictive lung disease or a PRDS, it will not go more than 6 ml per kilogram tidal volume. So 6 ml per kilogram, so if it is 400, it will increase the RR in such a way that it is achieving 7.5. So it will go from some lower RR to higher RR. That's why you get a flop sense like this. Are you understanding? The RR is larger, and this is very the tidal volumes are around 6 ml. That's how it does that. Okay.
So this is the Woodridge formula. So exactly on this algorithm it works. So where the rate is equal to the constant divided by the time constant what we have, which is the inspirator resistance into the compliance. So this part of respiratory time constant becomes very important to also monitor in the machine. So when we talk about the normal time constant, any idea what is the normal time constant? So it is around 0.6 seconds. So when it comes to the time constant, it usually take for one breath to complete. It usually take 0.6 seconds to complete that one breath, and so almost around 3 time constant it takes to finish the entire cycle of the breathing. So which I will be showing in the subsequent slide. So what exactly is time constant? So the respiratory system time constant reflects the speed by which the system changes its volume in response to the change in the applied pressure. So it is exactly resistance into the compliance. What we are going to achieve is the time constant. Now in terms of the inspiratory and expiratory time constant, so exactly at the 3 time constant we achieve the 96% of the volume inside or the entire inflation of the lung. So here are the 3 time constants. So where you will see that there are short time constant in the restrictive lung disease because there will be relatively low compliance. So if you see here that the compliance is 22, which is very low, and as per that the time constant is less than 0.6. Here for normal time constant it should be between 0.6 to 0.9, where your compliance will be around 60 ml per centimeter of water along with the respiratory resistance of around 10. For the obstructive disease, again we will have a high inspiratory pressure, okay, and we will have a high compliance, okay, which will give us a long time constant of more than 0.9 seconds. So this is how exactly we can monitor the time constant, which is because it is going to give us the entire respiratory mechanics. Because when it comes to analyzing and monitoring the respiratory mechanics, time constant is the best thing, which was I think not there in other machines. And in Hamilton, we are able to see the time constant and understanding the respiratory mechanics easily. Yes, we do used to have the compliance and the resistance, then we should calculate probably and then understand the time constant.
Well, understood this or not?
Kind of.
What did you understand? Okay.
I have talked about obstructive breathing.
What is the time constant first?
Time constant is the multiplication of resistance and compliance.
What exactly does that mean?
Resistance means the
No, so it actually means, what does time constant actually mean? It says, how much time will it take to inflate the lung to 63% and how much time it will take to deflate the lung to 63%. This is all that it says. Okay, it says that मेरे को 63% lung फुलाने के लिए कितना time लगेगा? This is what is time constant. Are you understanding? So it is obvious that if you are having an obstructive lung disease, it is going to take a longer time to inflate the lung, so you will have a longer time constant. Similarly, if you have a restrictive lung disease, it will have a shorter time constant. The inflation and deflation. You understand?
Yes.
You understand? Because it's poor lung compliance, so it will rapidly fill the lung. So the time constant will be much lesser. It is just the volume that you are filling in 63%. Total 63% कभी fill होगा. That is what is time constant. You are understanding now?
So exactly for
So
the
what will happen if there is a decreased inspiratory, if there is a decreased time constant? क्या होगा? What exactly is happening? So issue is what, you know? Entire issue about time constant. Why is it so interesting? Is your time constant of each of the nebula is different. You know, it's not so simple. इतना सिंपल नहीं है कि भाई टाइम कांस्टेंट को लंग का पता है, क्योंकि तेरा टाइम कांस्टेंट ये लंग में और ये लंग में डिफरेंट है. एक ही लंग में दो अलग में अलग अलग टाइम कांस्टेंट होता है. If you know your time constant, you know how to ventilate. That is the point. If you know your time constant, you know how to ventilate. Because if you know how much speed to give the breath or how much speed to remove the breath, I will be able to adjust my pressure and the volume. It is how much to inflate and deflate, isn't it? 63% inflation, 60% deflation. If I know that time constant, I know that how. So normal time constant is actually 0.1 to 0.2. Multiplied into 3 times, 63% deflation, ना? 63%. So 3 बार अगर 63% का 63% का 63% हुआ, तो वो 97% पहुँचेगा. You are understanding? So normal time constant is not 0.6.
in the range of 5.
No, you understood what I'm saying?
Three constant.
Three
you are taking
no.
out.
So,
So according to
three
the
time
three
constant.
The second is 0.6.
Right.
You understand? समझ में आ रहा है? The time constant is 0.1 to 0.2 seconds. I don't require more than that to inflate and deflate my lung to 63%. But I don't want 63%. How much I want? 97%. I want 90+%. No. तो अगर मेरा टाइम कांस्टेंट 63% है, सेकंड टाइम कांस्टेंट जो बचा हुआ लंग है उसका 63% है, देन द नेक्स्ट कांस्टेंट इज 60% ऑफ दैट बचा हुआ लंग. तो 3 टाइम कांस्टेंट लगेगा मेरे को, 3 to 4 टाइम कांस्टेंट लगेगा जब तक मैं लंग को 97% इन्फ्लेट करूंगा. And the 3 is 0.2 into 3. That's why you get 0.6. समझ में आ रहा है? हाँ?
So here exactly on the ventilator monitor we will be able to monitor the time constant. Okay. So you must have seen by now on the ICU. And in this year the normal time constant mentioned for the compliance of 60 and the inspiratory pressure of 10. So if you talk about here the short time constant, so you see here a picture which is just given 0.19. And it is mostly you will observe it in ARDS conditions. Yes. Yeah. So if you see this is a lung. Here we have again a different tool for monitoring, which is called dynamic lung. So in the dynamic lung we see the airways, okay, for the inspiratory resistance, and for the patient effort we see the diaphragm coming here again in the way. So exactly we are able to see that in the monitor. Okay. So when the patient takes the inspiratory effort, okay, we'll be able to see the diaphragm coming in, blinking in here again. Similarly, for any sort of obstruction, okay, you will see a red marking lines inside, which shows that there is a increased resistance. And in this also, if you see, this is a normal lung water, okay, and the actual lung is little closer, okay, less. In that case, it is showing it is a restrictive disease. So it is showing you in terms of the visual monitoring, it is showing for the inspiratory resistance in your airways, okay, for the compliance in the lungs, okay, and for the patient's inspiratory effort or trigger, you'll be able to see that here a small diaphragm again coming in and going. In case if it doesn't trigger, it will not come.
So if there is pleural effusion like that, so
No,
it will
so-
show restrictive. Means pattern it will show us some.
Pattern it can show, but it will not give direct visualization of the pleural effusion. I mean, we cannot relate it to the EIT part, okay, visualizing the fusion.
What about that thing? That's what I was telling somebody. Somebody asked me, how many efficient I was saying, no, this is just a diet. And doctor was saying, there is a lot of food in the lung and all. Arey, how are you just looking at everything and talking everything? ऐसा हो गया था.
So same thing explained for the long time constant. So here you see we have 1.04, which is too long for the obstructive.
So I actually want to understand from this machine how am I able to judge my accurate time constant? You know, that's what. See, because now you would have understood. If you have the time constant in your hand, you know how your I ratio should be changed. You understand, no? Because take the example that the patient is in obstructive airway disease. So he's going to take a longer time to fill, because he's got lower volume. You know, he's got a bigger volume. So he's going to take a longer time to fill. So my inspiratory time has to be high, and my expiratory time also is going to be high. You know, you understand? Because it is going to take a longer time to empty also. In fact, it will become more longer time to empty because it's passive. Active versus passive aa jata hai. Whereas when it is a restrictive lung disease, your time constants become smaller. So the I ratio and RR will change accordingly. You know, so now you must also understand now that when I talk to you about plateau pressure, you now understand what the time constant means now. Why it is 2 seconds? Why do you have to hold for 2 seconds? If you now think, why do you have to hold for 2 seconds? Because if you hold for 2 seconds, at least some lung will approximate. बाकी सब इसका time constant, इसका time constant, इसका time constant सब अलग अलग है. तो 2 सेकंड में at least थोड़ा तो approximate होगा वो. You understand? थोड़ा तो approximate होगा time constant. समझ में आ रहा है? Point the highest limit of time constant is 0.2. No? Are you understanding? And that's why now you must also understand why plateau pressure is not right pressure. You now understand why plateau pressure is not right pressure? Because time constants are different for each alveolus. Your plateau pressure is monitored when flow is 0. When flow is 0, you're going to monitor plateau pressure. When you press inspiratory hold, you're making the flow 0. There will be certain alveoli that are still empty because they have a longer time constants. There will be certain alveoli that are already finished empty. At the end of the day, your flow is not 0. That is why sometimes when you do ARDS patients, the plateau pressure takes a very long time before you get a graph that is straight. तुमको समझ में आ रहा है what I'm talking? समझ में आया कि नहीं? समझ में आया? So each alveoli has got a different time constant. So there will be one alveoli that is so big, there will be one that is so small. ये alveoli का time constant अलग है, ये alveoli का time constant अलग है. जब मैं plateau pressure दबा रहा हूँ, तो मैं क्या कर रहा हूँ? मैं flow बंद कर रहा हूँ. जब मैं flow बंद कर रहा हूँ, मेरा pressure तो मेरे को यहाँ से monitor करना है. जब flow नहीं है, तो यहाँ का pressure और यहाँ का pressure एक ही रहेगा. This is what I'm assuming कि भाई flow नहीं है करके, flow नहीं है करके. Flow अगर आ गया, तो I can assume that no. अभी क्या हो रहा है? यहाँ पर 4-5 alveoli और है, जिसके time constants अलग-अलग है. These may be deflating even slower, so it is still having a flow. So your plateau pressure may not be the right pressure.
So instead of holding for 2 seconds, 5 seconds.
We don't know. It can be 5, it can be 2, it can be 1, it can be so on an average only. That is why it is an average. That is why the pressure, plateau pressure is an average. That is why I don't take the plateau pressure as 30 to be adequate. Take it as low as possible. So if you are seeing a 29, don't be happy. I want to get it to 25, I want to get it to 20. That is what your thinking should be. And certain time will come when suddenly we'll say, plateau pressure should be 20, should be 90. That's why on the evidence pyramid, tidal volume comes first. On the evidence pyramid, low tidal volume ventilation comes first. Because that we know for certain is very clear that it increases that there is a problem. Plateau pressure comes down on the evidence pyramid because this is the problem with plateau pressure. You're understanding. So that's why if you don't even monitor blood pressure, it becomes really really bad. अगर तुमने blood pressure monitor ही नहीं किया है, जो है वो भी monitor नहीं कर रहा है, then you feel that what are you monitoring? So if your patient is on the ventilator and you have not mentioned plateau pressure, I feel यार ये उनको समझ में नहीं आ रहा है कि at least plateau pressure तो पता करो. So when you are ventilating, when you are writing your notes, ventilation में blood pressure नहीं है, you feel अरे यार इसको blood pressure नहीं देख रहा है. Because I want to know what it is. No, you want to know what it is. If it is 30, it is normal, but I want it much lower. You understand? Huh? You understand? Yeah.
So then again, it comes to ASV. So ASV is there since very long. Okay. So exactly it launched in 1998. Okay. So at that time it used to work only on the Otis formula. Okay. And the standard volume in the ICU, which used to be, which the algorithm used to set, is in between 8 to 10 ml per kg, okay, or almost 9 ml per kg. But then again, it has relaunched in year 2016. Okay, where they have come with the new volume part, which is 7.5 ml per kg for the ideal body weight, and it is based on both Otis formula and the Meets formula, as explained by Dr. Laga in her slides. So this is exactly what we have right now is ASV 1.1 version in the machine. So again, this is I guess explained by her in terms of Otis formula and the Meets formula. So we have two elements in common, which is the time constants and the alveolar ventilation and the dead space ventilation. So this was the observational study. It was a study done in terms of the volume and the change in the pressure. Okay, where we have taken normal lung, ARDS lung, ARDS moderate lung, severe lung, and COPD lung. So there were around 120 patients which was taken. So exactly when the mechanical ventilation is associated, we know that it is associated with the lung injuries because of the stress and strain. So moreover, the ventilator-induced lung injury can be prevented by limiting the driving pressures and the tidal volumes. So the ASV algorithm determines for a given minute volume the respiratory rate and the volume combination associated with the minimum work of breathing. So plateau and the total peak. So if you see here the plateau and the change in the pressure, and these are the volumes which have been achieved for the normal lungs, 7.5 ml per kg for the ARDS mild, moderate, and severe. So it can be achieved as low as 6.6, and moreover for COPD it can be achieved at a higher range also. So this study was done and they have calculated all these things. So ultimately the peak plateau and the total peak were measured by the 5 second in the end of the inspiratory and the end of the expiratory occlusion pressures, and the change in the pressure was calculated. Okay, which was the difference between the plateau and the peak. Okay, which is mentioned in the first slide.
So it's maintained the plateau pressure and it's maintained the driving
pressure. So it maintained the plateau pressure and it maintained the driving pressure here, as mentioned in the study. So ultimately, what exactly we say here is that ASV is able to select the lung protective ventilation, okay, with the limited driving pressures in the passive patient in the intensive care unit, okay, as per the differently lung condition patient. So this was a study done and proven, which talked about the change in the volume and the pressure. So now comes to defining the targets and the limits. So exactly what we are doing, we are also calculating the ideal body weight. So we are setting the height in centimeters, patient gender, okay, and after that we are going to set a target minute volume in percentage. Okay, so 100% as expressed for normal lung. Okay, so the user has to set the minute ventilation in percentage based on the target PCO2 levels. Okay, so of course ABG becomes still important when it comes to intensive care setting. So we have a ABG and we see that if there is hypercapnia or severe hypercapnia and you want to accordingly change the minute ventilation, you can do that. But if it is a normal lung, if it is a PCO2 in normal range, you can always set a 100% volume as a starting setting and accordingly change the same. So when we say we talk about closed loop, how exactly it is working. So these two are defined by the clinician. So we are setting the target minute volume in percentage, and we also set the PASV limit. Okay, and this PASV limit is 10 centimeters of water lesser than the peak pressure what we achieve. Now, exactly how when we attach to the patient, it gives first the 3 test breath, and with that 3 test breath, it achieves the best inspiratory pressure. Okay, the RR and the TI, inspiratory time. Okay, and based on that, it will calculate the respiratory time constant with the compliance and resistance. Okay, and it will also measure the patient spontaneous activity by the RR and the volume. So this is from the patient part, breath by breath. So, but for that, when we attach, as I said, that it is going to give 3 test breaths to achieve that best possible 3 values of
So this is a knowledge-based system. So I don't know, there are another ventilator setting called as PRVC on the ventilator, pressure regulated volume control. So all these work on the same principle. So whenever you do any measurement in the ICU, let it be ultrasound, let it be compliance, let it be plateau, you always do 3 measurements. You always do 3 measurements because 3 measurements ka average is what we actually look at to understand the measurement. So what does it do? It actually gives you a breath. The ventilator puts a breath. It puts a breath to actually find the compliance and the resistance. What does the ventilator do? It gives a breath. It gives a pressure targeted breath. And with that, it calculates the compliance. It finds out the resistance. Now that it knows the compliance and resistance, it puts it into the Otis formula. Okay, and then the Otis formula does it continuously. This is what occurs. My question was, how much time does it do this? I want to know how much time does it do this? Or 3 breaths you karte hai? Once in a day, only 3 breaths are done?
No sir, initially when you set the target minute volume percentage, so that time it will check for all these things. Anytime after you change any settings related to target minute ventilation, it will also try to re-verify that the tidal volume and the rates are accordingly the patient respiratory mechanism.
So what we should do is, in our existing ventilator is happening, we just should change the ventilation and see whether they're actually giving those 3 breaths. If it's giving those 3 breaths, then we know that this is how it's working.
after every change of minute ventilation.
Okay. So this is knowledge-based communication. So something from there goes to understanding this is going back.
So again,
So it also depends on the target. Basically, when you see the ASV graph, there is an actual plotted target which is there, and there is a plus sign, which is the current measured value. So as and when you change the minute ventilation to make sure that the target and the current value match each other, based on that also it will
No, we don't need to change that. We will never be changing that. In adaptive support ventilation, I am not changing anything.
No, sir, you will change the minute ventilation.
I will not change based on that graph. That graph is only telling me that the ventilator is doing its job.
Of course.
I will not change that. I will not to get the plus into that box.
No.
I will not do anything.
No.
The plus and the ventilator does everything to get the plus into the box.
Right.
Okay. What I am doing is I am only changing my minute ventilation depending on the frequency, spontaneous breaths that are there. That's the only thing depending on how the patient is doing.
Yeah, what I meant is, depending on the ABG also, when you, for example, you want to do target minute volume setting based on your ABG reading, you want to increase it or decrease it also based on the spontaneous activity. What machine will try to do is target and the current value will try to match based on the changes.
and the graph will try to match it.
It will always not the same because it will depend on the setting also.
Okay, let's do it. Yeah.
This plus sign. And there's a target. So whenever you're going to change, the machine will try to come and meet this target point to achieve that.
Yeah. So what I'm trying to tell you is, I am not looking at this point. The machine is looking at this point. If I have to look at this point, then it defeats the purpose of adaptive
So as per when you change,
we don't
do
try to do matching of this.
This
Change the settings
machine
based on the actual target.
automatically. If the point convincingly comes outside here and does not come back here, means there's something wrong with the patient here. We need to quickly take care of this patient.
Yes. But for that evaluation also, it will try to do a test breath again, and then it will check whether.
Yeah, probably it will do it every time it goes out. Maybe I don't know.
Yes.
So that one of the policies of this is the problem that it gives high RRs. And the I ratio is completely dependent on the time constant. So that makes it a little bit difficult because very often you get 1:1 breaths on ASV.
Yes, most of it.
Very often you get 1:1 breath, which is kind of inverse ratio. very often now you get punished by the time, because the time constant of every area is different, no? So when it does this time constant business, I used to, if you next time you look at ASV, you get punished on almost all events. So what happens?
So as we said that 3 test beds were given by the machine and it has achieved the best possible efficiency values, and this from the patient side, putting this in the British formula, we get this in on the machine. Similarly, how it works with the closed loop is that again with the ASV algorithm, it will calculate the optimal target RR and the volume. Okay. With that, it will adjust the mandatory rate and the inspiratory pressure. Okay. And ultimately, again, it gives putting it in the British formula, we are going to again get the best possible time constant. So this is exactly how it has shown in circle to understand the closed loop. So defining targets as explained. So here, say suppose we have a patient where we calculated the ideal body weight of 66, and with for adult patient, so we have taken a coefficient of 0.1, which calculated around 6.6 liters of the minute ventilation. So here the target volume is 424 with a rate of around 16. So automatically the machine will adjust. Now, like how sir has said, whenever we have a plus sign, so whenever we change the minute ventilation, it is going to come. It is try to come near the target point which the machine has decided. Also to explain all the zones, so what this white square is the safety zone. Okay, if this box is vertical, then it may indicate also barotrauma or volutrauma. However, it may also resemble to the disease part, which we are going to talk about in the next slide. Then auto breathe can be also observed if it is too extreme right. Similarly, dead space ventilation, okay, and the apnea part if it is not triggered. Now here is the safety box, what we always say. So if your plus sign is ranging in this box, okay, coming in this box, that means your minute ventilation is achieved. Okay, not totally, but it is at least safe. Okay, but if this is going outside the box, okay, that means it is not safe. And automatically the square will also change. It will turn to a rectangular vertical form or a horizontal form. This is a ASV safety window, and so this was for normal lung what we have seen right now. For the low compliance in the stiff lung, you will see a horizontal rectangular. For the obstructive disease, you will see a high resistance and a long time constant. So this is something we are going to see. So these are the 4 things what we.
You said that safety box will also change. Suppose if it's a barotrauma, why should the safety box?
Safety box, no, it will. ये बॉक्स नहीं आएगा उसपे, खाली जो कर्सर है ना वो चेंज होगा.
नहीं वो विंडो भी दिखेगा.
Box will change. So what happens?
Box will change.
So what happens is, how is the safety box calculated? The safety box is calculated based on the pressure of the compliance and the resistance. So compliance and resistance dekhega wo. So if the compliance has actually suddenly gone down, what it does mean? It means that the lungs volumes have actually gone down. The time constants will change here. Okay, so at that moment it will actually figure out that this is not safe for this patient because compliance has changed.
No, if there is a barotrauma or a volutrauma.
Again, obstructive जैसे लिखेगा वो. It will change as per what your compliance is. No, if your resistance compliance changes, your box will change. You understand? It is trying to figure out that box based on your compliance and resistance. You understanding?
So suppose the compliance is
The purpose of the safety box is basically to avoid the apnea, to avoid the over distensions and avoid obstructive. जहाँ पे obstructive है वहाँ पे giving higher respiratory rate. So depends on the lung mechanics, the safety box will change, but it will make sure that any of your the box, I mean the target plus, we need to it's more of a visual indication that जो target है is out of the box, and we have to kind of change the settings so that slowly, gradually the target or the current value.
Like for example, let me give you an example. Okay, you have a patient who is on who has come in and you put 130% minute ventilation. Now 130% minute ventilation रखा, इसलिए उसने एक बॉक्स बना के रखा कि ये इस बॉक्स पर रहना चाहिए. उसने डिसाइड करके तुमने 130% बोल दिया. Okay, now what has happened is this patient starts developing autopsy.
Yeah.
This patient starts developing autopsy. So your box will actually is supposed to be like this, no? Your plus side will keep on coming outside.
Yeah.
then it's like you are out ventilating outside the box. If the ventilator is taking a long time to come inside this box, understanding is developed an autopilot. So it will try to do this.
So safety box will stay there only, na? That's what.
So what will happen? Safety box will remain there
The
only.
target only will move out.
Will change, but then that is what I asked him.
But then
That is what I asked him. That how frequently it is actually doing the breath.
Yeah.
You understand? So that will probably change the box. What she's asking is, does the box change?
Because when he
No.
said the box will change, that's what I'm
Box will change only on the basis of the time constant
Time constant.
and the lung condition.
That's what I'm
It
saying.
will not
But if
change
there is an
gradually
auto-keep-
all the time.
That's what I'm saying, that when it auto keep or parrot auto, the box should not change. The target will change.
The box will change.
The box will change.
Box will-
Because what is going to happen is, as it is figuring out the compliance and resistance, it will change. The time constant will come to know. With that, it will understand that the auto peak is changing, this is changing, that is changing. So it might change. It might change.
So the compliance come and the patient is going more restrictive. So the safety box will change to bring the target to less.
Yeah, exactly. That's the entire point I'm asking. Ki, how many times does it do the test breath? Because the entire point is that only does it do the test breath very often? What is the criteria to give the test breath? That is the question that.
Right. Also in this presentation, the point of having those slides is that how the safety box changes as per the lung condition. So I mean, if there is a confusion, every time the box will look different, more or less it will not look different all the time because it will be having probably one condition or mix of both. So depending on that, you will get a general safety box, which is more of a visual indication that this is the frame in which the lung positive ventilation will happen, and probably you are out of that frame. So your settings might depend on that, how soon you come into that.
But we have attached for the normal lung patient ICU. So it always remained in the middle because it was of normal lung and no lung condition. So the entire time the safety box was at the same place. So how to use ASV? So the main thing, the absolute contraindication comes is the leakage. Okay, the ventilation with leakage, and specifically so NIV we are not using this mode. Okay, so it is not recommended for NIV, and moreover the bronchopleural fistulas if there are, okay, then we are not also, because it will again increase the leak part. Okay, and so for that reason ASV is contraindicated in these two conditions, and the related contraindications would moreover be irregular respiratory drive in case if the patient has any. So measuring the height of the patient, okay, we are already seen that we are going to first measure the height, and as per that we are going to calculate the ideal body weight. So these are the controls what we have seen in the ASV. So the passively patient ventilation. So we are going to set the percentage minute ventilation is equal to the target minute ventilation. So as said that it ranged from 25% to 350%. Okay. And when we set 100%, that means we are going to achieve 100% of the minute ventilation of that set ideal body weight as per the coefficient. So then similarly, it can increase, decrease to reach the target PaCO2. Okay, and the initial setting would be from 100 to 110%. Okay, for the normal lung conditions. For the spontaneously breathing patients, you can also achieve the minimum minute ventilation. So you can decrease the minute ventilation, okay, if you get the patient's spontaneous activity, okay, and it will again decrease to change the level of pressure support. Then other two settings come is the PEEP and the FiO2, which is the usual one. So PEEP, you will start with 5 centimeters as the initial PEEP setting for the patients. And of course, if you have restrictive or ARDS patient, you can start it with the higher PEEP of around 8 or 10. FiO2 settings, it can be again adjusted as per the PO2 and the SaO2 range as per the blood gas. So initial other parameters. So those were the three main control variables which is on the screen visible. If you go to those controls again, you will get other control options as well, which, as I said, is one is the PASV limit, pressure ASV limit, okay, which can be set around 30 centimeters of water. Suppose if you want to set the alarm limit of the P inspirated pressure 40 centimeters, we usually set that. So this ASV limit should be set around 30. Then we have of course inspirated rigor, then we have expedited rigor sensitivity and the pressure range. Now weaning, when it comes to weaning, we of course have to see the screening and criteria for the weaning, and we need to see that how much the patient is ready to be taken off from the ventilation. So all other hemodynamic parameters we of course have to observe what we are anyways doing in terms of patients, blood pressure and other stuff, fever and having secretions. All that thing comes additional, but moreover when it comes to the respiratory part, as you will see the spontaneous activity and you will be able to reduce the thing. So again, daily screening will be something which we have to do. Okay, then weaning trial which includes our SBT, okay, which can be done in the machine, and then extubation with either a high flow, okay, or a NIV. So here is the weaning criteria or vent status. Vent status basically help us to analyze that how fast our patient is ready to wean, or whether our patient is ready to wean or not. So this vent status includes the patient's oxygenation status, the levels of PEEP set, the minute ventilation, the inspiratory pressure, and the percentage of spontaneous breathing. Okay, so it's little blurred, not visible very well. Okay, so all this points. If this, you can see this bars. If this bar is in the white range, okay, that means this is under the normal range, and the patient is not. I mean, if it is above the white range, outside this white range, this bar, that means the patient is not ready to wean. So we need to observe this vent status completely, which includes our oxygenation, our percentage of spontaneous breaths, okay, and the minute ventilation, which is already achieved. But you can see the minute ventilation in liters per minute here, whether he is achieving in that target minute ventilation or not. And similarly, you can also do so these are the some parameters which can be observed. Moreover, you can see the screening phase in the ASV graph. Okay, again, I'm checking for the safety box. Okay, so if you see here again that this plus sign is almost near to the target range. So that means also the patient is available to wean. So this is in back picture. If you see, it was not inside the range, it was outside the range. No? So here, if you see, it's almost outside here. Now, if you see the next picture, it is inside the range. All the bars inside the range. Okay. So exactly when it comes in this, okay, it starts automatically the SBT, okay, and then it will give for around 30 minutes.
30 minutes.
30 minutes.
After that, it can give a status message that consider extubation or something.
So it will give you status measure and the message that consider for extubation, but looking at other criteria, of course, for the about the tube obstruction, all the things, secretions, fever, and other stuff you will have to anyways see, even if it is in this state. You were asking something?
Means yesterday when we had a patient, it was going on for like 2 hours, no? So
What?
the SBT, the time
No,
it had,
just keep on going on.
no, they are saying that it will display a message.
No, it will not show extubate. It will just keep on displaying 2 hours, 3 hours, 4 hours.
That's what we know.
Unless you go on to an SBT.
There was
Where is that?
option.
So what will happen is, see, as far as I found the G, they also have a very similar model. Hamilton G what? G1, Galileo 2, or what is it called?
G5.
G5. So in that, what they also had some very similar things. Okay.
Yeah.
So what happened was when graphics were different. So when this comes into this bar and all of these remain adequate, and how do they calculate this adequacy? If the pressure, inspiratory pressure is less than 15, if the PEEP is less than 8, if that's what is set here. That is what is set here. FR2 is around 40%. So when all these things, which are our standard extubation parameters or standard weaning parameters, when they come in over here, that is immediately automatically sometime it goes into this timing, and then the timing will keep on occurring, keep the time will go normal level.
Yeah. So there are two things. For example, now we are using only ASV along with the vent status. So once all the parameters are in the defined range or the inside the white boxes, it will start the timer.
Yeah.
For 30 minutes, if you see that these parameters are still inside, that means your SBT is probably successful, and then you can consider it. We have also another mode called IntelliVent ASV. It's another automation which is brought into ASV. In there is a SBT trial which you can actually run, and
weaning with Intel ASV, it gives you indication that now your SB trial is successful. You can consider extubation.
So this is about weaning. Now, how do you adjust it if the patient is in distress? What about that? So if you have a patient, like the other day you were telling me that the RR went up, patient became distressed. What you should have done? You just increase the. Yeah, so if the patient's distress is increasing, if the patient looks distressed, just increase the percentage support of minute ventilation.
That day also I increase the minute
So if it's so how do you do it? By steps of
10%.
20%. Because 20% only change something. 10% will not change anything. If you want to change something, at least 20% you have to give. 5 or 10% करके क्या मिलने वाला? So if say for example this patient was on 100% minute ventilation, and then after some time you found that the respiratory rate from 20 has gone to 25, 30, and he's looking distressed. Then you don't think I'm going to change the ventilator, I'm going to do this, I'm going to do that. नहीं सोचना है. We just increase the minute ventilation by another 20%. So if it's 100, make it 120. Wait for some 2-3 minutes. Wait for some 2-3 minutes because it is going to immediately affect the patient. You can see the difference. It's not like patient घर में रहेगा. अगर समझ लो after another 5 to 10 minutes, patient still remains like that. You can't leave the patient. 5 remains like that. What do you do next? Increase it by another 20%. That is why you have the range up to 350%. That is why you have the range up to 350%. You understand? So keep increasing it. Okay, till you reach that the patient is now not distressed. So what also you can understand is by looking at the respiratory time constant there. What is happening there? Respiratory time constant देखिए you have an idea. RC expiratory जो आता है उसमें. It's a number that comes in the monitoring. So you see the RC expiratory, you will understand what is happening there. If your respiratory time constant is going lower and lower, you can understand that the compliance is worsening and worsening. If and that is why your RR is becoming increasing or decreasing or whatever depending on obstructive or restrictive pattern. So we are looking at your expiratory time constant, which is this machine is calculating. This is the only machine that is calculating this. You will have an idea what is happening to the why this RR is going up or why the RR is going down or why the time volume is going up or going down. You understand? So healing is simple, but tackling the distress is a little bit difficult because you have to stand with the patient and go up.
Yeah.
That's the point. But still, it is much easier than otherwise. You only one parameter changing. You cannot change anything more.
So in the red we have seen that it was out of the bar, and in the yellow we have seen that it will automatically start a timer for the SVT, and when it is almost about to end, it will start the SVT at that time, green range, and it will run for around 30 minutes, and then we can observe that it has successfully, if he has done the SVT, and after 1 hour, then you can extubate the patient. So ultimately, what is the conclusion for this? That this ASV mode is easy to use ventilation mode for managing respiratory patients, especially for intubated patients, and it is able to select a specific breathing pattern based on the patient's lung mechanics, as per the extended time constant. Because with that we measure the patient's lung mechanics, and moreover, it is able to select the lower volumes as per the allocatic weight and change the pressure according to the latest recommendations for the ARDS and the normal lung patients.
So I'm actually very happy that Siddharth and Akash came here to put that ventilator there because it actually it's not just the use of ventilator, it's also understanding physiology.
By understanding this mode, there's a lot of physiology that we've understood here today. If you see, we've understood time constants, we've understood a few things in physiology that makes a big difference here. And so each ventilator, don't take it that it's just a super class ventilator like that. It also gives you a lot of physiology understanding. So now you have a new thing that you can look at when you're in the ICU. Isn't it? There's something new that you can look at in the ICU. Thank you, Akash and Siddharth, for coming here. And let's use this ventilator more to understand what's happening. Okay.